Okay, so we did 4-1, which is exponential. So today we're doing 4-2, which is logarithmic functions. And the reason they're together is because they are inverses of each other. So this says no horizontal line can be drawn that intersects the graph of an exponential function at more than one point. This means that the exponential function is 1-to-1 and has an inverse. The inverse of an exponential function with base b is called the logarithmic function with base b. Alright, so logarithmic functions are going to look like this. Your base is going to have to be bigger than 0, so no negative bases, no bases of 0. You have to take log of a positive number, so that x, the guts, have to be greater than 0 also. And your base also cannot be 1. And it's the same thing as b to the y equals x. So if I have y equals log base b of x, it's the same thing as b to the y equals x. The way that it was shown to me when I was in school is they said that it's like a little circular pattern. Log base b of x equals y. So I would get log base b of x equals y. So the base stays the base. What was the exponent becomes the answer, and what was the answer becomes the guts. So like x and y like switch places and the base stays the base, but the log goes away. Alright. That's really all we need. Alright, so our goal is, can we go from one to the other? That's the first like little baby thing. So the base is 7. Logarithms were invented to find exponents that are hard to find. So that means that the answer to a log is the exponent of an exponential. And then the guts become the answer. Alright, so for b, you have log of base b, so your exponential has a base of b. B squared is 25. Alright, and then this last one, you're going to have 4 to the y equals 26. So base of 4 to the y equals 26. Here we have base of b squared equals 25. Here we have base of 7 to the third equals x. Alright, so going the other way, if I give you the exponential, can you give me the log? So this would be log, remember the base stays the base, so we log base 2 of x equals 5. Log base 2 of x equals 5. Logs find exponent, so the exponent is the answer to the log. Alright, so this one's going to be log base b of 27 is equal to 30. Log base b of 27 equals 30. Here we have log base e of 33 equals y. And we'll talk about this more later, but anytime you have log base e, that's considered the natural log, and we write it with an ln. So we can just write it as ln of 33 is equal to y. Okay, so logs are another way to write exponentials. They're a way to find exponents. That's really why they were invented. If I told you to figure out what the exponent was, if I said 2 to the x equals 8, you could figure that out because 2 times 2 times 2 is 8. So it would be that 2 to the third is 8. But if I said 2 to the x equals 6, there's no way for you to figure out that exponent. Lots of guessing and checking, and you would just have to get like as close as possible. So what we're doing with logarithms is being able to find exponents that we wouldn't normally be able to find. What we're going to do on this page is if you take the log and you write it in exponential form, you should be able to evaluate what it's saying. So if I write this as 10 to what power is 100, then I figure out that the answer is 2. 10 squared is 100. If I write this as 5 to what power is 1 over 125. Well, you know it has to be negative because that's how you make a whole number become a fraction as a negative exponent. And then you also can figure out that it's got to be a 3 because 5 to the third is 125. So it would be negative 3 is the answer. Alright, for the last one, we're saying 36 to what power is 6? Well, the relationship there is you want to take the square root of 36 to get 6. And remember that square root as an exponent is 1/2. Alright, so some basic log properties. Log base b of b equals 1. Because if I rewrote it as b to what power is b, your exponent would be 1. That log base b of 1 equals 0, because b to the 0 power is going to be 1, because anything to the 0 power is 1. So in order for me to get 1 as the answer, I have to have an exponent of 0. So what this is boiling down to is anytime you see this number and this number match, the answer is 1. Anytime the guts is 1, the answer is 0. Alright, so some more properties. If log base b of b to the x is going to equal x. So if this says log base b of b to the second, the answer would be 2. If we have b to the log base b of x, then the answer is x. So, moral of the story is if your bases match, the exponent is the answer. If your bases match, then this extra number is the answer. Alright, so here you have log base 7 of 7. If you say base 7 of 7, then that extra number is the answer. So this is equal to 8. It's just that number. Alright, if I have this one, you see how you have matching bases. So this 17 is the answer. Alright, so to graph a log, we're going to do one in a minute to practice because that's what most of your homework is can you, or part of your homework, not most, can you graph a log function? And they don't really put a whole lot of examples on here. So I'll do some. Right now we're just wanting to say, can you give me a graph of f of x equals 3 to the x and log base 3 of x. So for this one, you're going to make a table like we learned in section 4.1 with negative 1, 0, and 1. Plug in negative 1, you get 1/3. Plug in 0, you get 1. Plug in 1, you get 3. And when I say plug those values in, I'm saying put them in the place of the exponent. So 30 to the negative 1 is 1/3. 30 to the 0 is 1. 30 to the first is 3. Alright, so if we plot those points, we get this graph right here. Alright, I'm telling you that these are inverses. So if you just switch x and y on those 3 points, you'll get your graph. But how I want you to graph a log, you're going to make a table. But what's going to happen is you don't know how to evaluate this. So, well, actually you do because you have a calculator, but it works out better if you arrive it as 3 to the, we'll call it y instead of g of x equals x. And then we're going to plug in negative 1, 0, and 1 for y and get x values. So we get 1/3 here, 1 here, and 3 here. So you see how these are just reflections of each other. You just switch the x and the y. So we have a point here, we have a point here, and we have a point here. And you should notice that we have 2 graphs that are reflections of each other over the line of y equals x because they're inverses. Now, for the exponential function, it has a domain of all real numbers and a range of the asymptote to infinity. Well, since we switched x and y, guess what? Domain and range switch. So our domain, my color didn't change. So our domain is now going to be from your asymptote, which is the y-axis, sorry. And your range will be all real numbers. We go forever up and down. that we have to start here and go that way for the domain. All right, so how do you graph a log if there's a weird transformation? So here's your example of that. So let's say that I give you y equals 2 plus log x minus 1, and we'll make it log base, we'll just stick with 3. All right, so we're going to just write it as a basic exponential. So to get our graph, we're going to say 3 to the y equals x. None of the extra numbers are going to go in there. We're going to make a table. So we took this basic log right here. We load it in exponential form. We're picking -1, 0, and 1 for the y's. So we get the 1/3, 1, and 3. Then we know that this tells me to go up 2, because that's a +2 on the outside. And we know this tells me to go right 1, because it's a -1 on the inside. All right, so to graph that, you are going to graph the original. So this is what it looks like without shifting it. And we're going to make our adjustment. So we're going to go up 2 and to the right 1. We're going to go up 2 and to the right 1. Sorry about my pen. We're going to go up 2 and to the right 1, and then redraw our picture. And just like with those exponentials, you've got to remember that we moved, so our asymptote moves. And with what am I talking about? With a log, when you move left or right, that's when your asymptote changes. So this is going to not pass that 1 mark. All right, so we have a domain of 1 to infinity, and we have a range of all real numbers. All right, so the domain, hopefully you have picked up on the fact that the domain, that this value comes from right here. If I had a negative log function, then it would go the other way. So I'd have to say negative infinity up to my asymptote. Okay, so the next thing is, can you just find the domain? It doesn't ask you to graph, it just wants you to find the domain. So this is a positive function, so we know that the graph is going to look something like this. And we know that the asymptote is going to move to 5. So our domain is 5 to infinity. So with a parenthesis, because 5 is the asymptote. We're going to get really close to it, but never actually be it. All right, so let me draw this in just a little bit better. So this is completely in the wrong place based off of that. I'm trying to make sure that when I print the notes, they make some sense. So I want this picture to be there and to look nice. Hold on, let's go back to black, and we'll put some more points. And then, and our picture was supposed to go something like that. Alright. So next, we're going to talk about a common log. So common log is when the base is 10. Our number system is based off of 10, so that's why they consider it to be a common log. And when you're using your calculator, it's the button that just says log. So if I want the base to be 10, I can replace it with just regular log. So I just want you to know that this is the same thing as this, and we call it a common log. All right, so an example of using that, and this is where you're going to want your calculator, And it can be a graphing calculator or it can be your cell phone calculator if you just turn it sideways, like turn your lock screen off, turn your phone horizontal, and you'll get a log button. All right, the percentage of adult height attained by a boy who is X years old can be modeled by this function, where X is the boy's age. So it's important that we know X is their age. F of X represents the percentage of his adult height. So approximately what percentage of his adult height has a boy attained at the age of 10? All right, so we're just going to say F of 10. So we'll do 29 plus 48.8 log, that's the log, so 8 log of 10 plus 1. So then with our calculator, we're just going to type that in exactly like it looks. We'll do 29 plus 48.8 and then hit your log button, which is, if you're on the graphing calculator, it's in the first column of buttons right next to the 7. And we're doing log of 11 because 10 plus 1 is 11. All right, and we get 79.82 as the answer. So he's 79.82% of his adult height at 10. All right. Excuse me. All right, so next page. We have properties of common logs. And they're the same properties that we've talked about. If you have log base b of 1, it's 0. So log base 10 of 1 would also be 0. These properties are really no different from these properties. So I don't really know why they gave them to you as a separate thing. You don't need to write them all down. This is also not something I'll write down. It's just saying that whatever the exponent is the answer. So if you would rewrite this as 10 to a power, you'll see your answer a whole lot easier. All right, so a natural log. We had this show up a minute ago. If something looks like this, we write it like this, and it's considered a natural log, the base of e. So we discussed the other day where e comes from. It's like 2.7. I don't want you to be like concerned with it or make it scary. People always do that, and I don't know why. E is just a number, but it's like pi, so we use the e button on the calculator when we're dealing with it. All right, so like the domain of all log functions, the domain of a natural log is still all positive real numbers that are bigger than 0. All right. So if I want you to find the domain here, so if we have this one, I'm going to rewrite this because you see how it's 4 minus x. Well, we want the x to be positive, but that's not really going to fix it. So if it said this, you would tell me that it was 4. Well, that's because if I make it equal to 0 and solve, I get 4, right? So if I have one that doesn't look like I expect it to look, I can always figure out where my asymptote is going to be by setting the guts equal to 0. So in this case, if I move x to the other side, I still get that x is 4. So we're going to say that the domain is 4. My gut says 4 to infinity, but if x is negative, then that's going to reflect us over the x-axis, so it's actually going to be negative infinity to 4. So again, because x is negative, that's a reflection over the y-axis, so this one is going to look like that, instead of going the way the ones we've previously done have gone. And it has nothing to do with the ln, it's just because you have a negative x. So we reflect over the y. Okay, so try this next one. This one is extra fun. This is ln of x squared. So again, if you say x squared is 0, then you get 0. So you have an asymptote at 0. But what's weird about this one, if you graph it in your calculator, then you'll see that it actually has like 2 pieces to it. It's going to make this picture and this picture, because whether I plug in a positive or a negative for this x, I'm going to square it and get the same answer. So negative 1 has the same as a positive 1, or a negative 2 for x is going to be the same as if I plug in a positive 2. It's both just take an ln of 4. So I get like 2 different pieces, and they should be symmetrical, but I can't tell. So our domain for this one is negative infinity to 0, and then hop over and do 0 to infinity. Alright, so here's the thing. If I'm asking you to find the domain of one and you're confused, graph it in your calculator. Okay, and remember that ln and log are buttons, so you can just go to y equals, type in whatever they give you, and graph it, and you can see what's going on. But your calculator, like on this one, they both go down forever, but the calculator makes it look like they just kind of stop right here, because for some reason it won't finish it out. Just understand that those have arrows and they keep going down forever and ever and ever. Alright, I believe that's it. Oh, nope. Alright. This is the same thing. Do not write these properties down again, because they're the same no matter what the base is. Why I gave them to you a million times, I do not know. Alright, so an example of using ln. If you have this formula, f of x is equal to 13.4 ln x minus 11.6. That tells you the outside temperature compared to the temperature inside of an enclosed vehicle. Alright, so it models the temperature increase in degrees Fahrenheit after x minutes. So we use the function to find the temperature increase to the nearest degree after 30 minutes. So the one is to find f of 30. So 13.4 ln of 30 minus 11.6. Now be careful, make sure that you understand that that 30 goes in parentheses, so it takes ln of 30 first, and it does the other things later. So again, in your calculator, where are we going? 13.4 ln of 30, close parentheses, minus 11.6, and you get 33.976, and they said to the nearest degree. So 34 degrees is how much it's going to increase in 30 minutes. So if it's like 96 degrees outside, that's really, really hot inside your car. Right now, I really do think we're done. Okay, so your assignment is, let me go find it. I forgot to type it on here. You're on page 489 and 490. And you're going to do numbers 3 through 30, multiples of 3. And then 54 through 72, also multiples of 3. And then 84, 90, and 98. Alright, if you have questions, please let me know. Make sure that you're trying to do the homework and asking questions so you're not too far behind when you come back.